with this, I would like to introduce our first keynote speaker, Reynold Xin from Databricks. So he's a co-founder and chief architect at Databricks. And he's essentially leading the development of Apache Spark at Databricks. He's responsible for numerous projects in the context of Spark, including the data frames API, which is for high-level data science, I guess, right? Yeah, okay, so he's going to talk about these things, of course. But again, most of the major innovations of Apache Spark have been led by Reynold, so I'm really excited to have him present the first keynote.
All right, thanks, Philip, for the introduction. Can I get a show of hands? How many of you have used Spark in the past? Okay, all right. So the second slide will be for those of you that just haven't used it, or in case you never heard of it. I'm going to be talking about Spark and Scala, although a lot of it actually focused on Spark itself, but interleaving in the talk, I'll be talking about what Scala enabled. And at the end, I'll talk a little bit about what I wish were designed slightly differently in the Scala programming language and the overall ecosystem itself. And happy to discuss some of the points after. Just in case you've never heard of it or you didn't know what it is, I put together a slide, because Philip told me, hey, just in case. So I put together just now, just very simple bullet points. It's actually a project started in academia in 2010 at UC Berkeley, and now it's the most popular and probably the standard for big data processing. And it's happened also to be one of the largest, if not the largest, open source project written in Scala itself. Although, while Spark is written in Scala, it's usually facing APIs in many different languages, including Python, R, SQL, and all of that. And a lot of the companies that I know actually started using Scala because of Spark. A lot of them started, for example, using the Python API, and they realized, hey, this thing is written in Scala, and there's a lot of new features that's only available in Scala. Let us actually use Scala instead. Right. One funny thing I saw from a while ago was, if you look at the Stack Overflow 2016 survey, so this is the survey that Stack Overflow did on 60,000 developers in 2016, and it turned out Spark and Scala tied to be the #1 factor correlated with high salary. So if you know Scala and you know Spark, there's a good chance you can skip your PhD, so just kidding. All right, and Philip's kind of introduced me. I'm one of the co-founders of Databricks and chief architect. For the last few years, been working on Spark for a while. I'm kind of proud of myself on as a matter of fact, the netlines deleted on the project. So while adding a lot of features, I also deleted a lot of crap from the project. If you go look it up, it's kind of hard to beat that metric. And I was doing my PhD at UC Berkeley for about 3 years in databases and been on leave since 2013 working at Databricks. And with that, so to give you, a lot of you probably know a hell lot more about programming languages and Scala than I actually do. My Scala experience actually just comes from mostly day-to-day working with it, plus with reading books from Martin and all of that. I did, before Scala was actually my first functional programming language, or semi-functional programming language. Before that, I mostly used C-like programs. And I also returned the Databricks Scala style guide to make sure with a lot of open source contributors from Spark and a lot of the employees, engineers we actually have at Databricks, they can follow a consistent standard. And that's actually a fairly controversial style guide among the Scala community, especially for example, the purists hate it because it's kind of taken the approach of Scala's a better Java. So your miles might vary, right? It's just what we found working for us. I don't have an actual background in programming languages. I've never actually even taken a class. My undergrad wasn't in computer science, so a lot of my perspective just on seeing how things actually work is not necessarily from first principle, all right? And What that effectively means is, I think Adrian Morris actually summarized that really well. So for example, when I'm programming, I don't think very hard about, hey, what's the covariant, contravariant programs. I just add pluses and minuses until it compiles. And the other thing to note before I actually start the main part of the talk is because I haven't been in academia for a while, a lot of what I've been working on, I'm not claiming any novelty at all. When I was in academia, every time I give a talk, a nicer grad student would ask me, so how does this compare with the X that's been done before, right? A meaner professor might ask me, like, wasn't this already done in the 80s? Now I'm in industry, I actually don't care as much whether somebody has done it before. What I care about is really what I can get my users job done sooner. And today's talk is roughly two separate parts. The first part I do a little bit of archaeology. For those of you that are less familiar with the data science or the database part, some of this will be new to you. And then the second part, I will be talking about actually what's happening in SparkLand, kind of echoing some of the archaeologies. So let's start with databases. How many of you heard of this thing called IMS? One guy put up his hand, or a few. So IMS, I was looking up on Wikipedia, was this thing done in 1966. As a matter of fact, it is still being used today, because databases just don't go away. Once it works, nobody wants to get rid of them. It is a hierarchical database. What that means is you actually group data, kind of naturally maps your brain, like human beings kind of map data directly in hierarchies. For example, we break a company down into, hey, there are different business units of the company, different departments within it, there are different teams on it. It's kind of a hierarchy. But one of the issues that actually came up with IMS is, hey, now if I want to move data from one location to another, or if I want to have many different parts of the hierarchy referencing the same set of data, for example, somebody's salary information might appear both in sort of the organizational structure as well as some other different HR database. It's now actually becoming very difficult to move. Right? So this paper came out, I think in 1970-something by Ed Codd, who became a Turing Award winner on the large relational model of data for large shared data banks. One of the very important sentence in this thing was, I'm just going to read it. Future users of large data banks must be protected from having to know how the data is organized in the machine. Most application programs should remain unaffected when the internal representation of data is changed, and even when some aspects of the external representations are changed. Effectively, what Ed Codd said was, applications should be protected, should be sufficiently abstracted away, so it's not a new concept. You want abstractions, abstracted away from the internals. So when changes happen to the underlying hardware, or maybe even underlying data layout, the apps don't have to change. Right? And that kind of gave rise to two fairly important concepts, I would say, underpinning relational databases. The first one is physical data independence, and the second one is a declarative query language. And it sounds really fancy, physical data independence, but really what it means is, hey, you want your application, the API you create should be sufficiently abstracted away that it doesn't actually, the application is using the API doesn't care about the underlying physical storage. For example, if you go from a hard drive to a solid state drive, you shouldn't have to rewrite your application. And the declarative query language is actually an important part in achieving physical data independence. If you think about SQL, I bet most of you have seen or used SQL in the past. In SQL, you select what kind of result you want logically. You don't really specify, for example, hey, should you be using an index lookup on a specific table, or should you be using a sequential scan on the entire table, right? The database itself tries to figure out, hey, what is the most optimum, or what database thinks the most optimum way to actually run a query. And many of this is actually due to the, if you actually translate what Ed said to a more modern setting, or more layman setting, what it really means is you have applications written in the 70s and the 80s. Many of them are still running today. So you actually want, or actually the simple fact is the business applications outlive the environments. they were created in. As new requirements might surface, underlying hardware have changes generations of new hardware has happened. And there's actually a lot of different ways you want the application to be performing better. As a result, people introduce, for example, indexing, column stores, and all this new kind of technologies in databases, while the application program largely remained unchanged. Usually when I give this talk, I actually ask people to summarize the pros and cons, but because when I added a lot more Scala content, I can't be too interactive anymore. Otherwise, it would take a lot of time. So I'm just going to summarize what you might like or might hate about databases. Some of the nice parts is it's actually declarative. Data independent is what from the original paper. It's actually working somewhat reasonably well. And SQL is a universal interface that a lot of people actually know, right? And a lot of tools actually talk about SQL. It's a lingua franca. But there's also a very obvious downside to the database, relational database approach to data processing. I think the first and foremost is actually SQL itself. While incredibly powerful, kind of the lingua franca for data, it's not a real programming language in most senses. And when I say real there, put it in quotes, because SQL is actually fairly Turing complete and all of that. But the real issue is it's fairly difficult to actually compose and build complicated applications out of SQL alone. If you have seen SQL, I've seen a lot of customers' queries in which there are 2,000 to 3,000 lines of SQL. And thinking about debugging that is just a nightmare on its own. And a lot of it is just not the language itself, but actually the tooling surrounding SQL. For example, there's no actually great unit testing framework. There's no IDEs that actually help you go step-by-step guide. The other big problem with relational databases is it's actually too, I would say, opinionated and inflexible. And what this means is if you want to use a database, the first thing you have to do is think about how you model the data. And in a large enterprise, that typically means if you're building a data warehouse, you get all the stakeholders from various different departments together and to talk about how you actually model and create a schema for all your data. That process itself literally lasts years. All right, so before you can even put data in, you spend years discussing sort of the model for the data. And then on top of that, there's no other way to query the data other than SQL. So this is, some of the more modern databases are actually changing and improving in this aspect, but this is some of the big issues with traditional relational databases when it comes to different applications than what it was originally designed for. Right. And then about 15 years ago, this whole trend of big data kind of started with 2 or 3 of Google's papers, right? MapReduce, GFS, the Google file system, and the big table paper. And it kind of sort of brought a whole new trend. And if I have to summarize the big data problem, many of them are actually echoing some of the things that relational databases actually didn't work as well on. For example, the first is there's new kinds of data companies are bringing in to their data storage systems and processing systems. For example, Google was trying to index the web. How do you actually fit that into a nice tabular form? The other thing is, due to the volume of data, at least back then, it was very difficult to actually fit. It's actually impossible to fit the web on a single machine. So now you have to start thinking about how do you scale out storage and processing. I'm just going to skip this. What Google came up with around the early 2000s was, hey, let's just come up with a new programming model. Rather than asking our users to be writing MPI programs and Java or C code that actually coordinate with each other, let's come up with a new restrictive programming model. Many of them call them the data parallel model to actually give it to our users. And this is a more restrictive model that allows you to do fewer things, which is later known as also MapReduce. And the way you define operations in data parallel model typically looks something like this. Right, here's an operation. Run it on all my data. For example, here's a map operation. I would want to increment every record by 1. Run it on all the records. Now, I don't care exactly where this job runs. I want the scheduler to be taking care of that. As the end user, I only care about my application logic. As a matter of fact, because some machines might actually go down, because some machines might be slow, feel free to run it more than once. As long as the results are idempotent, as long as I get back what I expect, feel free to run it however you want. And many of this is actually very similar to concepts in functional programming, right? You want mean mutability, you want idempotency, and you want composability of different functions. It's also actually very similar in some ways to declarative programming in databases. You specify sort of what you want, and then you ask the system to actually decide exactly how to do it physically. Any questions up until this point? All right. And then some professors wrote an interesting blog post in 2008. David DeWitt and Michael Stonebreaker, for those of you not familiar with the database world, those are two sort of extremely well-known professors in the field. And Michael Stonebreaker also is a Turing Award winner. I think got his Turing Award a couple years ago. What happened is the database world kind of, I would say, in academia, missed this whole big trend of big data and MapReduce, and looking from the database angle, they don't really get why you need this new programming paradigm. As a matter of fact, this is the way they summarize it, right? One is, actually, a giant step backward in programming paradigm for large-scale data applications, a sub-optimum implementation, not novel at all. That's the ultimate academic insult. Missing most of the features that are routinely included in the current databases. The truth is looking, by the way, they've since then taken down this blog post, so you actually can't find it on the original location. But what happened after this was the debate escalated on both sides, from just writing on the internet forum to actually having ACM Communications articles published in actually legitimate academic journals about, hey, it doesn't make sense on your side, it doesn't make sense on my side. There's a lot of debate that happened for multiple years. Many, many papers were written about this. For example, they would compare performance of a database on a single node with some MapReduce program on 1,000 machine and show that, hey, I can outperform, my single node outperforms your 1,000 node cluster. Why the hell are you doing this? So it's a bad programming model, it's a bad implementation, it's not novel, it lacks features, right? Why the hell would you use it? The truth is both sides are pretty correct in their sense. Google, there's no databases back then that could actually work for Google's use cases. And there's no database, certainly if I want to dump my production logs, there are even terabytes of data right now. It's not a great location to put it in a database. But if I want to run some business intelligence applications, MapReduce is a pretty bad way to actually use it. And just to summarize, similar to how I summarize the databases, there are different ways to look at MapReduces, the pros and cons. The first and foremost sort of benefit of it is a massively parallel programming model in which programmers don't have to think about how to operate, for example, thousands of machines. At some point, I was an intern at Google, and on, I think, my first week, I wrote a MapReduce program that actually scanned the entire web and tried to mine some natural language processing phrases. That was pretty cool. It's impossible to accomplish in a relational database. It's a very flexible programming model. Essentially, it just says, hey, I'm going to give you 2 or 3 operations, and you define all your logic in the user code. It's type safe. So SQL actually doesn't have great compile time safety from perspective of the developer. From a perspective of the database, it actually has compile time safety because the compilation time of SQL is very different when you think of it as a database versus a developer. Developer think about when I compile my app, whereas database think about the first time I actually get the SQL query itself, I'm going to compile the SQL query. Right. MapReduce has pretty bad performance. If you want to use, both due to the implementation as well as due to the lack of features like indexing. So if you want to use MapReduce for a lot of kinds of applications that are typical in relational databases, the performance is horrible. The other problem with MapReduce, it's hard to capture from just looking at the literatures. It's actually extremely verbose. It's very difficult to compose. And a lot of this has to do with the essentially how the API was designed. And the classic example of this is, I think Google's original search index pipeline that runs on MapReduce was defined in 21 separate MapReduce steps. And each of the steps is a whole separate class of mappers and reducers, which are defined in different files, gigantic Java programs or C programs. There's tons of imports and boilerplate code. So when we actually look at it, look at the source code, you realize the actual logic for the indexing might only occupy 10% of the code. And when you look at some applications, if 90% of the code is not the actual logic of the application, it becomes very difficult to actually understand the application. So the other thing I want to talk about is R, Python, and data frames, which it's a whole new different domain now. I think this started getting pretty popular about 10 years ago with the rise of this new term data science. And with two primary programming languages, R and Python, and centered around this one framework called data frames. In some libraries, they are differently called, for example, data tables. And a data frame is really just it is just a table with a schema defined. So some tabular data structure with schema exposed to the end user. But what's pretty cool about data frames is there's tons of functions people have developed in the R and Python for all kinds of different data analysis. So if you think about, most of us are developers or engineers, right, or computer scientists. If you think about the way we reason about abstractions and computer programs, we think about what are the core primitives available in a programming language or in a library or in a programming paradigm, and how can I use it to compose higher level applications. For example, given a commutative and associative operation, I can easily produce a sum. Right? This is how a lot of us as developers think about how you can accomplish applications. Now, if you talk with non-computer scientists like statisticians, they don't think that way. They don't think, hey, how do I compute a sum? I'm going to break it into just running the two numbers and sum them up at some point with a reduce function. They think there's going to be a sum function somewhere that I can run, and the sum function would just give me the sum. All right? So that's exactly how essentially the data frame abstractions are done in R and Python. There's tons of functions about pretty much every single task you want to do. And if you're a statistician or if a data scientist want to compute some common task, most likely there's already a function written for you in the library itself. You just call it. Now, when it comes to traditional data frames, there's also some pros and cons. Some pros compare with, for example, SQL itself. It's actually built on real programming language. With R and Python, you could write loops. You could actually have IDEs. You have unit testing frameworks even. There's a lot of things that's actually very difficult to do in SQL. It's actually now doable fairly easily in R and Python. It's fairly easy to learn because as users are trying to accomplish specific tasks, they just Google or they Stack Overflow and they find some way to do it. There's also some disadvantages, I would say, when it comes to especially working with larger amount of data. The first is it's actually not parallel. Most of the R programs and Python programs, not even are they not distributed, they are not even multi-threaded on a single node. So I was actually trying to load about 100 gigabytes of data on my laptop, some CSV file into Pandas, which is the most popular data frame implementation in Python. And I waited for over an hour and crashed. So it actually doesn't work very well for medium and big data. So not even like terabytes of data, just maybe tens of gigabytes, hundreds of gigabytes. It might be very difficult to work with. And most of this are actually done, the underlying implementation are fairly simple, largely because of the way they only need to work with a smaller amount of data. So often they actually lack, I would say, sophisticated optimization techniques. Many of them I actually label here. They're very procedural and not declarative at all, which means if you actually ask the data frame API to compute, for example, an average, you compute the average as soon as you finish calling the average function. It doesn't actually care what you're going to be doing with the average later, because in some cases, for example, maybe I don't even to computing the average, or maybe there's actually a cheaper way to compute the average by doing query optimizations or compiler optimization in some way. Another one I didn't list, it's sort of neither a core nor a pro, is there's no compile time type safety, because Java and R and Python are actually there's no compile time. It's actually not even static typed. The reason it's not a pro nor a core is it depends on your use case. If you're doing some interactive analysis, sometimes you might even actually prefer not having any type safety at all. You just want things to work, you're typing, you don't want to declare what type it is. As a matter of fact, you might reuse the variable and use it in a different type later. But when you're actually trying to design a large data engineering application in which multiple different departments or different engineers on different teams who don't even communicate with each other on a daily basis want to stitch together, type safety is actually fairly important because it's part of it's part of the signature, it's part of the contract of the functions or the libraries you're actually using. You don't want somebody, you don't want sort of a big application to fail at runtime because you try to cast a string to an integer and the format doesn't match. All right, so at this point, you might ask, is this still a talk about Spark? What are we doing here? So I'm going to go to Spark. Next slide. Now, just a question for you to think about, right? So which one's better? We talk about three whole different paradigms. There's relational databases, there's sort of a data science world of R and Python, and there's the big data world of MapReduces. What's the ultimate paradigm? Which one will win in the long run? Spark will win. Why would Spark win? All right, just think about this. So as I was preparing slides, I dug up some old slides from 2013, and this is how we were introducing Spark back then. And this is the same year Databricks started. So we introduced Spark as a fast and expressive cluster computing system interoperable with Hadoop, and focus on two things. One is efficiency, basically speed of the runtime. The other one is usability, which is kind of the speed of writing the code. This is the two important part. And if you think about it, you have seen the more recent Spark slides. It's now introduced very differently. A lot of the users initially come to Spark because back then, hey, it's 100 times faster than whatever you're using before, which is MapReduce. That's great. They got attracted to Spark by the performance claims. But most of them probably actually stay due to the API because it's, the program written in Spark is now a lot more concise than if you were writing MapReduces. And the truth is the initial focus was really just what it was. It's, hey, you have this MapReduce runtime in Hadoop. You have the storage layer. Storage layer is pretty good. It's pretty good to dump a lot of data into HDFS. But now if you want to analyze them, it's incredibly painful with MapReduce. We give you a better MapReduce. It's faster to write and it's faster to run. So the initial API in Spark is called RDD, Resilient Distributed Data Sets. It is effectively just logically a collection of data, very similar to just a Scala collection. Except it works on a set of machines rather than a single-threaded program. And it's, as a matter of fact, it's heavily inspired by the collection library itself. So here's like three examples, 3 lines. You could, for example, so Spark itself is a Spark context. It's a entry point to Spark, and you can call a text file to actually load, for example, some text file. And the resulting collection lines would be a collection of strings. So 1 line per string, or 1 line per element. And then you can call, for example, a map function, filters, and count. If you go look up the API, it's very similar to a collection API itself, with the exception that there's more auxiliary functions for working with keys. So different, for example, you could do a group by and reduce by key. Because in big data world, the reduce in MapReduce wasn't really just commutative, associative through the whole collection. As a matter of fact, it's grouped by key. So you want to pivot your data by some key and then start doing reductions on it. And the implementation was just, as a matter of fact, it has some pretty simple implementation back then that I would say decent ideas that may, or even just reasonable ideas compared with MapReduce that actually make it a hell of a lot faster. For example, scheduling decisions made just with a single RPC round trip versus in the original Hadoop MapReduce implementation. Scheduling a task, you're not scheduling immediately, but you're waiting for the next heartbeat between the nodes to actually send the RPC. Here's like one example, just to visualize the complexity. The hello world big data is word count, essentially counting how many times each word appears, right, in the big corpus of data. And here's how you write word count in 50 lines of a Java MapReduce without the import statements. And here's how you write it in Spark. If you're familiar with functional programming, it's fairly easy to grasp. And there's actually a lot of questions after we started the project on, hey, why did you guys pick Scala? As a matter of fact, many users early on told us, hey, we're never going to use you because you're using this weird programming language called Scala, and we are Java shop, or we like C shop. Why the hell would you do that? And I mean, in hindsight, it's a great decision. We chose Scala kind of based on, I would say, 3 reasons. The first is we wanted a JVM-based programming language because back then, think about it, we were pitching Spark as a better MapReduce. So interoperability with Hadoop was extremely important. And Hadoop itself was written in Java. And as a result, all the Hadoop ecosystem and all the libraries were in Java. If we pick a non-JVM language, we would have to actually re-implement, even, for example, just how to read data from HDFS. And just given a couple developers back then, there's no way we wanted to do that. The concise syntax was extremely important. This has to do with the one I briefly mentioned before, which is we wanted the application to look like actually an application full of the actual logics rather than boilerplates. We don't want, for example, a lot of declarations of boilerplates. If this is a mapper, this is another mapper, this is a reducer. We just want the code to look like what the user is trying to express. And then the interactive REPL, we kind of realized early on, hey, data analysis on its own is actually a very iterative process. You typically have to actually write some snippet of code. You run it on the actual data to see what it does. It might crash because the data is coming in a slightly different format from what you expect. You have to tweak it, and you have to finally arrive at maybe your actual final product, and then you turn it into a more rigorous engineering job. And the iterative aspect was very important. So we wanted a REPL that the users could quickly iterate on. Now, there's also some challenges with the original Spark API. It was a much better MapReduce. In 2013, it became very clear. And 2014, I think, is the year that actually most of the Hadoop vendors started integrating Spark into their offerings and for some of them, it became the primary offering and completely kill MapReduce. 2 challenges also we saw from working with a lot of users. The first one with the initial API is I would call lack of structure. And what I mean by structure here is sort of schema. Data, the vast majority of data are structured. It means you have different fields in your data. They might be nested structure, so it doesn't fit into a relational, like tabular structure, but that's structured. Like JSON is a very structured format. Even if you're working with unstructured data, for example, images, at some point you're turning your images, if you're doing machine learning, into the vector, a bunch of vector of numbers. That's still a structure. The RDD API is sort of just a collection of something. And if you want to impose structure on that, you have to think about defining classes, which in the Scala case would be case classes. But defining a case class for every single step of your program actually led to also a lot of verbosity. Right? You think about, hey, if I'm just doing a slight transformation of I have a line, I want to chop it into different fields. Now I have to declare a new case class for all those fields. If I'm just changing the semantics of one more field, now I have to declare another case class. And what we found is most users don't bother defining a lot of case classes. And what they do is they use this magical concept or this great utility in Scala called tuples. But then we realize, hey, our users' programs are littered with _1, _2, _3, _4, and worse. They nest them. And that's very difficult to understand also. The other program is as the users are, the user base is growing, it went from sort of just data engineers over to data scientists. And again, engineers think about abstractions, they understand functional programming, they've probably taken like Lisp or scheme classes back in college. Data scientists never even heard of this term. And now to introduce map and reduce to them, it's kind of a very foreign concept. Now one example to illustrate this lack of structure is, this is a very simple program. How many of you could tell me very quickly what it's doing in 10 seconds? All right, show the result. I did, the only person I've showed this code to and who actually told me in less than 10 seconds what it's doing is a guy that's a PhD from Stanford in computational math. Now, how many of you can tell me what this is doing in 10 seconds? It probably doesn't need 10 seconds. All right. And we'll come back to this. And the second challenge with the RDD API was performance. The RDD API is essentially, hey, here's a collection of some domain-specific object user-defined classes. And then the users write closures, Lambda functions, and we'll run them. Now, it turned out most users don't write high-performance code. And if you write idiomatic functional code in Scala, and you run them on billions of records, most of the time, the overhead actually dominates the actual computation needed. And this has a lot to do with how the thing is designed, has to do with how the user write them. For example, the collection API and the RDD API also under the hood is implemented as iterators, right? It turned out when you are, for example, doing some computational light program, like just summing up a bunch of numbers, the iterator calling next overhead is actually way higher than the computation itself. So probably 99% of the time it's actually in overheads. As a matter of fact, even a node check is more expensive than just incrementing a bunch of numbers or summing up a bunch of numbers. And the object allocation could actually kill the whole system due to garbage collection. So it's actually hard for users to write performant functional code. And the other problem is, hey, we also have this API in Python and R. We created, we essentially implemented a different front end for Python in which we take the user's Lambda functions in Python. We try to run them. And the JVM communicates with Python processes using sockets. And while Scala programs weren't the most performant, the Java program, or the Python programs are way worse because they interpret the language. So here I'm just going to show you one very simple demo. Can't be simpler anymore. This is sort of the Databricks user interface that we give to some of the users who are data scientists. And it's really just a Scala REPL, right? You could call like val a equals, hi. You can type arbitrary Scala programs in here, and it will actually run it. It runs it on an extremely powerful cluster that has 6 gigabytes of RAM here. Here's a very simple operation you can do in the RDD API. What it does is it just parallelizes a collection. Under the hood, it doesn't actually materialize the elements. It just finds the beginning and the end boundary of this a billion numbers. Sends you a cluster. Here, I'm running a map function convert to a long, and then I just do a reduce to sum up a billion numbers, right? It's a very simple application just to visualize. For example, if I'm a user and I want to sum up a billion numbers and I run this, what would happen? All right, so I'm running now. Spark chop it off into actually 8 separate tasks. So this is running in 8 separate threads. I have a very lightweight cluster of single node under the hood. It's running, running, running. And what it's doing is it's turning each number into a long and then sum them up. And it took about 16 seconds to sum up a billion numbers. All right. This is the Spark's new API, which I'll go in a bit. Here, what I'm just writing in a weird way, but effectively, I'm giving Spark the expression that I want Spark to run, which is just summing up a bunch of IDs. And it took about 0.5 seconds. They're doing exactly the same operation. This is mostly running user code. This is running something I'll explain in a bit. But it went from 16 seconds to 0.5 seconds. As a matter of fact, most of the 0.5 seconds are still overheads because this is a very lightweight computation. I'm actually doing a lot of threading and all of that. If you actually write something on your laptop, don't write it with Clang though. Clang would actually optimize it into a direct. It returns you the result immediately by turning it into a closed loop, closed form solution. But if you disable that compiler optimization, you realize it actually runs even faster than 0.5. Right? So that means, hey, you could actually achieve summing up 1 billion numbers as fast as 0.5, maybe even faster, right? So when the users write this program and it took 16 seconds, the majority of times there's overheads.
Why are the answers different?
Are they? Oh, the first one didn't include the exclusive and inclusive at the end. Thanks for pointing it out. That's actually that's the wrong. Yeah, now it's the same. Yeah, great catch. Still took about the same time though. The actual number didn't hurt. I can skip this. So just to remember the two issues we saw. One is the lack of structure, and functional transformation are as intuitive some of the users. And the second is performance. It's hard for users to write performing code. So the solution we came up with is, I think around 2015, is about just 2 years ago, is this whole new set of what we call structured APIs in Spark. And we kind of did both Spark SQL and data frames together. Data frames is a new abstraction. If you've used Spark in the last couple of years, you probably use data frames. And Spark SQL is what you think is running SQL queries on Spark. We actually had a whole paper published on this topic in SIGMOR 2015, so you can actually look at more details of it. Although a lot of the internals are actually now obsolete, like that paper is obsolete about internals. But think about it as the structured APIs. You have SQL on one hand, and you have the data frame API on the other hand. And both of them are just generating some intermediate representation called logical plan for computation. So if you think about you writing SQL queries, typically a database parses the SQL queries and turns them into some syntax tree. And then what the plan there is actually called a logical plan. So same thing happens with data frames. The data frames API is in many ways just a programmatic way of generating the logical plan. And then there's actually a query optimizer. So the front end and the back end is fairly decoupled. There's actually a query optimizer that optimizes the logical plan, very similar to how you would how it works in relational databases, and then turn it into a physical plan. And there's a code generator that turns the physical plan itself into RDDs. If you don't have database background, a big difference between the logical plan and physical plan is the logical plan just specifies the logical operation. For example, a join is a logical operation, all right? But a physical plan specifies what kind of join it is. You might have a nested loop join, which is a simple nested loop to run the join. You might have a hash join, which builds a hash table for one of the tables, and then you perform you loops through the other table, do the hash lookups. This should be a hash join. There's many different join physical implementations. So each of them will be a physical operator. And the logical operator is just the join itself. The optimizer will have to choose, for example, hey, with this kind of distribution of data, what's the best physical join implementation I should be using to be running this logical join. And here's what sort of a data frame API looks like. You could actually ignore maybe the first line. You could actually run arbitrary SQL statements in Spark and have it return a data frame API, data frame. And then the second line sort of does a filter. And you might think sort of the syntax is a little bit awkward. Why the hell are we doing this? with sort of an apply function that passes a filter. And the reason is this actually matches exactly if you were to do it in R and Python in a data frame API. So for data scientists using Python as a programming language, they will actually write this very natively in Python, except it's a square bracket. And then the whole API design in a way that unless it also allows you to run declare user-defined functions, but most of the expressions are actually expressions that Spark understands what's going on. For example, this equality predicate, we're doing it through operator overloading to tell Spark, hey, this is actually running a equality predicate on the users table. And then it just builds a whole plan that's transparent to Spark, and Spark now understands it and can actually execute it and optimize it. So if you think about RDDs, it's all the programs are written by the user, essentially. User define every step of the operation is user defined functions. And then if the user defines something in Scala, we have to run it in Scala because it's a Scala closure. We have to run it in the JVM. If the user defines something in Python, we have to run it in Python. We can't run that portion of the user code in the JVM. There are Jythons out there. It doesn't work with most of the user functions. But if you look at the way data frames are executed, now unless you define still the user-defined code, which allow you to do, but if you use any of the built-in functions, they all just generate the same logical plan under the hood. And it's actually being executed in the JVM itself. So you have sort of a shared backend and different front ends now. As a matter of fact, if we go look at the implementation of the Python and the R API for our data frames, it's substantially simpler than the RDD API because all it's doing just simple wrappers around the logical plan representation. And here's sort of an example of how it's executed. I don't have enough time to get into all the details, but here's like one simple program. Here's what you construct as sort of a plan that's optimized. It's a join, and in this case, you can tell, for example, the optimizer did a very simple thing, which is there's a filter here, right? Which actually happens after the join, as the user specified. But in the actual plan, we could push the filter beneath the join itself. So the optimizer is actually doing smarter things to avoid, for example, blowing up the join. Because the joins are more expensive. Running the filter after the join is actually more expensive than running the filter before the join. And because logically they're equivalent operations, we could push the filter down. This is a very simple optimization. And then the way it's executed is actually there's a whole code generator that takes this plan and takes the physical plan of it and generates very low-level code. And the low-level code looks like while loops everywhere. There's no iterators, and there's no iterators. It actually specializes things as much as possible. If we know, for example, it's an integer, it's just an integer. There's no like java.lang.integer. There's no extra null checks. Strings are actually always encoded in UTF-8. There's no longer immutable strings. And there's all kinds of crazy things when you want to do with performance optimizations. The code generator does that for the user, rather than having the user do it. And there's actually it's hard for you to see it, but there's a paper in VLDB 2011 by Thomas Newman from TU Munich on efficiently compiling efficient query plans for modern hardware. The Spark code gen approach actually follows that paper. So if you think about what Spark has become after doing this, Spark effectively becomes a compiler. It looks more like a compiler than actually a database or a big data processing framework. Right? There's front ends, there's back ends, there's intermediate representations, there's generating code. And Scala is actually, in many ways, even though maybe the Python API for Spark has overtaken, for example, the Scala API, because there's more data scientists out there than data engineers. It's actually Scala play an even more important role here, which is it's a hell of a lot easier to write the compiler in Scala due to, for example, pattern matching and case classes and libraries defined for tree manipulation than any other language out there. As a matter of fact, we had a lot of discussions on, hey, we can rewrite this part of Spark in a different language, but the thing that's really difficult to do is actually the compiler part. And after the data frame API, things look pretty great. A lot of data scientists love it. But then we got complaints from data engineers. And what they told us is, hey, the RDD API, sometimes I crash my system due to bad memory management because Spark doesn't understand what the objects are. The data frame API doesn't crash as often, but I don't get my type safety anymore. If I'm building a large data engineering pipeline, I don't want Spark to fail at runtime to tell me, hey, the type mismatches. I want my compilers to be giving me, again, the type safety checks in the contract of my functions. How can you help me do that? So we started another effort called the Dataset API, and which actually building directly on top of a data frame API with user defined functions. And Dataset API is a new API that looks very similar to RDDs. And it's very similar, and again, now it's a logical collection of some domain-specific class that user defined called dataset. For example, in this case, I have a dataset of string. You can call just read.text as string. And then you can do similar things as RDD API. What's different is, you can't see this at all. What's different is it runs on top of the same engine as the data frames, except it also, we've seen a new concept called an encoder. And what an encoder is think of it just a special data structure that describes the user class. For example, we have an encoder written for all the case classes in which we automatically get through context bound, so the user doesn't have to declare them or specify them explicitly, as long as it's case class or as long as it's Java beans. The encoder just uses reflection to actually look at the declaration of the case classes or Java beans. And then it actually generates how, for example, you can serialize the data from a user-defined class into the internal representation of Spark. For example, if the user has a string, I have to convert the UTF-8 internally encoded string into the UTF-16 strings that Java expects. That one is too dark and you can't see it, but what I want to show is just some context-bound declaration of a map. And this API is now actually becoming also fairly popular for people building large data engineering pipelines, replacing the original RDDA's API. All right. So the structured APIs in Spark is actually just a new, think of it as a multifaceted API for the very different big data use cases. There's SQL still, which is if you want to connect your BI tools to Spark, you could use the SQL API. There's R and Python API and the data frame API built largely for data scientists. And then there's the dataset API with its strong type safety built for data engineering workloads. And it's actually fairly complicated internals that I'm not talking about today. You can look at the source code or look at the SIGMOR 2015 paper to find more about it. And one fairly interesting thing with this is now with the decoupled front end and back end, it's actually we could use Spark or creatively use Spark in different ways. For example, you could actually think about Spark just as a very simple multi-core library for handling collection of data on a single node. As a matter of fact, I was just testing last night and realized, hey, I could already process CSV files or JSON files on my laptop way faster using Spark than using a lot of the toolings in the Python ecosystem right now because of the multi-threaded nature of it. We could actually take the same front end, the same API, and actually generate different backend code to incrementalize computation to make it a streaming engine. We could actually, I think one of the talk today actually takes the Spark API and that just generates actually native code. So Spark is running as with a native backend, even though it's using the different existing front ends, all using the same API. Right, just the last part of the talk. I realize no perfect language out there in Scala that got us a very long way. But in the last few years, I kind of wish there's a few things that would be designed slightly differently in Scala. Some of them I understand is maybe actually impossible to change because there's different trade-offs. But just want to talk about them so we can at least discuss them. The first one is actually binary compatibility. I'm probably not the first one to complain about binary compatibility of Scala. Every version upgrade has been painful. Now, this is actually extra painful for a service provider like Databricks we are running a SaaS service in which users give us their jars or when they interactively type in something, it's usually okay. When they usually give us their jars, as you saw before, the database programs that are written in maybe the 70s, they're still running today. We have jars that declared 5 years ago that users want to run today. If we were to run those jars, we have to support whatever Scala version they were writing. So concurrently, we have to support many, many different sub-Scala versions with different set of bugs in Databricks. But it goes more than binary compatibility. Some of the utility classes or utility features in Scala actually made it, while great for internal use, it's actually fairly difficult to ensure forward compatibility in practice when you're using them for create end-user APIs. For example, traits with default implementations. Sounds great for internal use, but if you were to use that as an end-user API, any new function you add for the future that adds another default implementation breaks the user API. Right? Case class is the other example. Adding a new field in case class is virtually impossible to guarantee. Nothing breaks from user's point of view. So it's not just backward compatibility, it's also the forward compatibility part. The other thing is Java API. Even though Scala is extremely popular, especially among Spark users, I think more Scala users than Java users, I do think as the Spark becomes more and more mainstream and get picked up by the rest of the developers, I would say, in the US west of Sacramento, east of Sacramento actually, which basically means outside of Silicon Valley, we will see more and more Java users. So Spark has always treated the Java compatibility as one of the topmost project goals. And this means almost everything has to be declared twice. Because the collection library, for example, is different. You can't return a seek to a Java user. And due to some bugs in the compiler, we always have to declare the test twice, too, to make sure it's actually callable in Java. I think Kotlin has something interesting, which is they actually just choke the Java collection library entirely in the language. There's probably actually some other trade-offs you have to make here. The other funny one is exception handling. And then here's where the purists will actually hate me a lot. Because why would you do track exceptions? And the reason why you want to think about that is, to me, it's inevitable to interface or interact with a lot of Java libraries because there's many of them that are written, especially for I/O and for networking. You could actually write a whole different one in Scala, but the Java ones are typically more robust. There's a lot more eyes on it. It's been out there for longer. And there's actually no good way to interleave the Java libraries with Scala to make sure exceptions are properly handled. And I could only think of two ways. We've tried both, sort of. One is you create a whole Scala shim for every single function the Java library has and make sure the user doesn't call directly the Java library. And you turn all the return types into tries to make sure you actually can properly force the user to think about them. Another one, which is uglier, and we have also done it, is we force certain modules that deal with low-level code. And the reason this matters more in the low-level code is if it's at a very high level, the exception bubbles the user might actually understand. But when it's very low level dealing with networking or disk corruption, for example, there's no way the user understands what's going on. So you don't want that original exception to actually bubble up. In those cases, we actually started writing some of the very low level code in Java to make sure we handle the exceptions properly. And then you sort of have a shim somewhere that meets in the middle. Right? And the last one is just tooling itself. And the tooling, there's a lot of different tooling aspects, but the one particular tooling I really wish for more is tooling to help enforce consistency on the project. For example, hey, we want to categorically disallow specific features, like some of the type level programming stuff. It has its use, but for working on this specific subset of the project, we don't want that. How can I accomplish that? I've actually personally written quite a few tools, quite a few rules for Scala style, but in general, it's actually very difficult to work with this kind of enforcement in the Scala ecosystem. So here's I'm really good at being on time. Here's the last slide, just to recap the talk. The latest Spark, in many ways, think of it as a multifaceted system or multifaceted API for the end user that to satisfy different use cases. And really what we have done is look at, hey, what are the different systems out there? How are people using it? Who are the personas that are using Spark? How we can come up with the APIs for them? And then took the best from all these worlds and make it. And Scala is it's a very critical part of how we've been building Spark, and also that's the end user-facing API. Thank you. We're also hiring. We might be running out of time for questions, but I'll be around for a little bit. Yeah. Thanks. Do you want questions, or should we break?
Yeah, I think there's not really time for questions. Maybe one.
So most of what you talked about is related to implementation based on relational data. I was curious if there has been any thought or progress towards implementation which can process data in different formats, such as a graph database, or specifically something like an RDF triple store.
Yeah. So I think the graph. So we had this actually a separate project called GraphFrame that we defined, and it exposes a new sort of a graph API. But under the hood, it's actually just backed by 2 data frames, one for the edges and one for the vertices. And I think, for example, Neo4j also implemented, they just announced it, a whole Cypher implementation on Spark, which essentially decomposes into different join operations. I mean, to me, you could think about graph internally 2 other ways. Right? One is if you come from a more numeric background, sparse matrix multiplications. If you come from a database, relational background, it's fast joins, aggregations. So you just want to be doing that very quickly.